And finally, we'll take a look at an algorithm that does guarantee maximum security. This is the Advanced Encryption Standard. The cipher was entered into the competition we mentioned. It was developed by two Belgian cryptographers. The Advanced Encryption Standard is also referred to as the Rijndael, from the name of its creator. The difference between the two is that Rijndael is more flexible. Some Rijndael-supported block size and key size combinations have not been certified by AES. The algorithm doesn't support these options now. The winning cipher was selected in 2000, over 12 years ago. Rijndael won over the ciphers Mars, RC6, Serpent, and Twofish. RC6, which we know about already, was developed by Ron Rivest, while Twofish, like its predecessor Blowfish, was created by Bruce Schneier, another big name in cryptography. Now, some details on AES. The cipher uses a key length of 128 to 256 bits. It encrypts data blocks of fixed 128-bit length. The number of rounds depends on the size of the key. The suggested key today should be 256 bits in length, although this mode is significantly less efficient than the 128-bit mode. There will be 14 rounds in this configuration. It's interesting to note that the Advanced Encryption Standard does not use Feistel's network. The structure that it uses is hard to talk about without an animation or a graphical aid. For now, remember that the round number is determined by the length of the key. Each round uses a round key. For each round, 4 diverse transformations will be performed. They are divided into layers. The first is the nonlinear layer. The next is the mixing layer, and the third is the key addition layer. The nonlinear layer is the crucial stage. As you already know from the DES analysis, substitutions are made in this layer to hide relationships between the plaintext and the ciphertext. So let's now take a closer look into AES. Before this, a couple of words on terminology. We'll use the term state. A state is the intermediate form in plaintext encryption, or in other words, it's the changing plaintext values at each stage of the AES encrypting process. States will be displayed as tables. Bytes of input messages will be in the intersection of columns and rows in the table. Likewise, you can imagine the key to be displayed as a table. The first transformation, the nonlinear transformation, is the most important one. It's called the sub-byte step. A substitution box is again used. And again, we'll locate a value of the ciphertext bits based on the values of the plaintext bits. This relationship is completely nonlinear. The second step involves shifting rows and moving columns. This is a simple operation that relies on shifting each row to the left and mixing each column. The goal again is to obscure any relationships between the key and the ciphertext. In each round, except the final round, rows and column positions are transposed. The final round involves only row shifting. At the end of each round, a key is combined with the state. The add round key operation is used for this purpose. The steps in total result in an efficient and very secure algorithm. The main appeal is the fact that it's a standard. If you're unsure which cipher to use for your solution, I recommend the Advanced Encryption Standard. No one ever got fired for implementing an adopted standard. Even if AES will in 5 or 10 years prove to have some now unknown deficiencies, which is unlikely because of one of the biggest strengths of public algorithms is that they're subjected to very intensive testing, you can always defend yourself saying that you have implemented the standard. You can't be blamed for failing to predict it to have some faults.